A very warm and soothing good morning everyone present here. I am Abhimanyu Singh from Gautam University. I am a final year physics to give my brief views on the topic of electrical structure and electrochemical performance of polyethylene oxide dope with the ionic liquid. My layout of my presentation, it will include introduction, motivation, methodology, result discussion and the conclusion part. So let's start with the introduction part. As we know that there are several difficulties to increase the production in storage and the energy distribution which are faced by the researchers around the world in meeting this energy demand. So in order to find the answer to these challenges, an adequate ion conducting polymer electrolyte is highly required. Also, a supercapacitor plays a vital role in meeting the inflated energy demand at a very higher rate. I am currently focused to meet this demand using the synthesis of ILDPE using the dopant for the supercapacitors. So as you can see, the solution to the energy harvest, the capacitors, they are different types, usually the metal film, ceramic, electrolytic and the tantalum. Next we have the next generation of the capacitor, which is the supercapacitor that we say, which is made from the porous electrode materials, carbon electrodes, and it has usually extremely high capacity. So the EDLCs based supercapacitors plays a very important vital role in meeting the inflated energy demand at a higher rate. There are several advantages in using the EDLCs supercapacitor, which includes its high storage capacity, long life cycle, high power density, good charge discharge rate, and etc. There are also several difficulties to increase the production, storage, and the energy distribution, which are faced by the researchers around the world in meeting this energy demand. So the supercapacitor, as you can see, the electrochemical supercapacitors, they are usually divided into three categories: electrical double layer capacitors, hybrid capacitors, pseudo-capacitors. So in order to find the answer to these challenges, I suggest that we can use an adequate ion conducting polymer electrolyte is very highly required. The ion conducting polymer electrolyte provides the low equivalent series resistance and hence increases the high specific power of the supercapacitors. Next, we have the polymer electrolytes. The polymer electrolyte is divided into three categories, basically the solid polymer electrolytes, liquid electrolytes, composite polymer electrolytes. For the synthesis of the solid polymer electrolytes, also I want to tell like why we are choosing the solid polymer electrolytes only, because as we can know from the as compared to the liquid electrolytes, the evaporation rate and also due to the leakage issues, we consider the solid polymer electrolyte to be the very best for the enhancing the performance of our electrochemical devices. So for the synthesis of these SPE, we use different plasticizers, we form different blends, composites, addition of ceramic insulating fillers, use of new dopants, low viscosity ionic liquids, and it has very few disadvantages also, which is the low ionic conductivity, which is the main part. But because of the freestanding film of this SPE, we consider this to be the best for the stability for our electrochemical devices. Next, we have the ionic liquids. Why ionic liquids? Because we are considering the ionic liquid dot polymer electrolytes for the supercapacitors. So obviously we have to talk about the ionic liquids. So what are ionic liquids? It is composed of the ions only with the low melting point below 100 degrees Celsius, non-flammable, non-volatile, thermally stable salts, and wide electrical stability below. Next, we have the ionic liquid dot polymer electrolytes. So we can use different types of the polymers for the synthesis of the ILDPE. We can use commercial polymers like PEO, PEVA, PMMA, PVPI, and different biopolymers also like ketosam, PAMMA, and different polymers. Next, we have the commercial ionic liquids which are present around us. Basically, we use the TCM, EMI, and TCM. In this presentation, I'm going to talk about this ionic liquid. So we know that the viscosity and the mobility are inversely related to each other, and it always prefer the conductivity enhancement. So the motivation of today's and in my presentation is to how we can increase the ionic conducting solids, because usually the ion conducting solids have very high conductivity ranging from 10 to the power minus 1 Siemens per centimeter to 10 to the power minus 4 Siemens per centimeter, and also it has very high capacitance in our electrochemical devices. So the methodology that I have used in this in my work is like the solid polymer electrolyte films. They were synthesized using solution cast technique. Firstly, the polymer electrolyte, the PEO, 500 mg it was used, and it was stirred in the methanol solvent at around 400 to 500 rpm rate for the overnight. Next day, we observed a very clear homogeneous solution. The Teflon petri dishes were cleaned efficiently, and different weight percent of the ionic liquid dot polymer electrolyte solution was poured in different petri dishes at 1 to 10 weight percent. The polymer electrolyte solution were kept at room temperature for 5 to 6 days for the complete removal of the solvent to get a freestanding solid polymer electrolyte film. Next, in the schematic, you can see that the electrical double layer supercapacitors was fabricated using graphite sheets as a current collector. The cornstarch biopolymers as a porous carbon was mixed with PVDF-HFP binder for making the conductive paste. The ratio of the carbon to binders was 80 to 28%. The electrodes were finally fabricated by the coating of the conductive paste over to these graphite sheets and was kept overnight at certain temperature. And finally, we measured the supercapacitor performance using the electrical impedance spectroscopy. Now we can see from the result and discussion part, the cool plot of the impedance spectroscopy at room temperature at a high frequency region was plotted on varying weight percent of ionic liquid ranging from 0 weight percent to 10 weight percent concentration in PEO matrix as shown in the figure. We can see that a semicircular spur is seen followed by a high at a very speedy rate towards the lower frequency region. The semicircular spur at a high frequency area corresponds to the parallel permutation of bulk resistance and capacitance of SPE freestanding films. The bulk resistance attributes to dielectric polarization and ionic movement in a polymer electrolyte. Additionally, a high at speedy rate towards the lower frequency area attributes ion transfer near electrolyte interface. Next, we have the conductivity measurement. The EIS spectrum of pure ionic liquid doped PO are analyzed as shown by the figure. By analyzing the EIS spectrum, the ionic conductivity of pure and ionic liquid doped PO are calculated using the formula of conductivity given by 1 upon RB L upon A, as we are very much familiar with this formula. This conductivity value is quite comparative as reported by the other researchers, where they got the value of 10 to the power minus 6 Siemens per centimeter. Whereas, as we can see with the increase of concentration in our work of the ionic liquid, we can observe a change in the order of conductivity, and hence at 8 weight percent of ionic liquid we have a optimized and highest conductivity at 10 to the power minus 5 Siemens per centimeter. This sudden increase in our conductivity might be due to the increase of the free mobile charge carriers during the incorporation of ionic liquid in the PEO matrix solution. Next, we can see from the dielectric spectrum that the value of the dielectric constant measurement tabulated in the given figure, and at three different frequencies, that is 10 to the power 3 Hz, 10 to the power 4 Hz and 10 to the power 5 Hz, marked with black, red and blue colors respectively. It is clearly seen from the figure that the value of the dielectric constant increases with the increase of ionic liquid concentration in a host polymer maintained up to 10 weight percent, which is due to the increase in the number of the mobile charge carriers and mobility of the ions. After 8 weight percent, there is a sudden decline in the value of the dielectric constant, which is because of the formation of the cluster of ions. Next, we can see that the structural and the functional groups of a material was synthesized, and it was confirmed using the Fourier transform spectroscopy and the X-ray diffraction technique. And also, we can see the thermal stability window of our sample using the TGA analysis. We can see that the TGA curve of pure PO matrix and the IL.PO are shown in the given figure. The weight loss at initial phase at 50 degrees Celsius to 100 degrees Celsius was due to the water molecules present in the PO matrix. It is clearly seen that there was no major weight loss in 350 degrees Celsius. Beyond this temperature, polymer PO completely degraded at 400 degrees Celsius, whereas in ion-doped PO matrix, as shown in the given figure, the SPE film was stable up to 380 degrees Celsius and completely degraded at 400 degrees Celsius. The increase in the thermal stability of the ion-doped SPE suggests that the effect of the ion on the thermal stability after incorporating with the polymer matrix increases by 20 degrees Celsius. At last, we have the cyclic voltammetry, which depicts the final electrochemical device result. The CV performance of the fabricated cell was evacuated at 50 millivolt per second on the voltage range of 0 to 1 volt as shown in the given figure. We can see that the CV profile shows a undistinguishable square shape hysteresis loop, which is basic feature of the EDLC. The deviation from the square shape in a CV profile suggests the equivalent series resistance which is present in the real capacitors. The calculated value of the specific capacitance shown by the fabricated EDLC at 50 millivolt per second scan rate on a voltage range of 0 to 1 volt reaches up to the final device capacity of 13.6 farad per gram, and we calculated by using the formula of C equals to I upon S. Next, we have finally the conclusion part, where we have successfully synthesized the ionic liquid 1-ethyl 3-methylene trimethanocyanide doped in a PEO polymer electrolyte using solution cast technique. The electrical and the structural characterization shows that synthesized polymer electrolyte is amorphous in nature. Finally, we have fabricated the supercapacitor device by sandwiching the optimized solid polymer electrolyte film in between the porous carbon electrodes, which shows the specific capacitance of 13.6 farad per gram at 50 millivolt per second on a voltage range of 0 to 1 volt. Thank you for your attention.